Okay, great.
Yes, you
So,
are.
okay, welcome everyone. So, I have been given responsibility to chair today's session. Today's speaker is Lực Ta from University of Pittsburgh, and he is going to talk about from affine algebraic racks to Leibniz algebras and the Young-Baxter operators. Over to you.
All right. Thank you, Dr. Singh. Yeah, my name is Look. I am a grad student at the University of Pittsburgh. And I'm going to be talking to you about my paper introducing some non-associative structures that I call affine algebraic racks and relating them to other non-associative structures called Leibniz algebras and solutions to the Yang-Baxter equation. Um, Right. So first, I want to thank professor at University of Pittsburgh, Bogdan Eon. This research actually grew out of like some final projects for some courses he took, and so I'm thankful for him. I'm thankful for John Marco La Rosa and Manuel Mancini for some communications about LIRACs. I'm thankful to my colleague Edison Helpman for providing the Beamer template for this presentation. And finally, I thank Dr. K-algebras, Dr. Singh, and all the other seminar organizers for inviting me to speak today. And below here is the main reference for this. All right. So today I'm going to start by discussing the problem that motivates these objects, affine algebraic racks. Then I'm going to talk about their definitions and some good examples. Then I'll talk about our main theorem in response to the motivating problem. And then I'll talk about some applications to Yang-Baxter operators. Um, yeah, since this paper is the first one introducing affine algebraic racks, there won't be like too much like structure theory or like hard like classification. It'll mostly focus on the main theorem and the applications to Yang-Baxter solutions. Okay, so the motivating problem is called the coquecigrue problem. I'm not pronouncing that right because this is a made-up French word. Um, but to introduce this problem. So this is the non-associative algebra seminar. So we all know what a Lie algebra is, but just to be on the same page, so I'm going to be working over a Brown field K. But most, if not all, of this stuff also works if you just work over an arbitrary commutative ring. Um, so a Lie algebra is when you have an alternating bilinear map, such that if you fix the left variable, then you get a derivation over that bracket. And that statement is one equivalent form of this identity called the Jacobi identity. So as an example, you have little gln, which is the vector space of n by n matrices, and it's a Lie algebra under the commutator. And so in particular, if you take k to be R or C, then you get the tangent space of big gln, which is the Lie group of invertible n by n matrices. And to show this, you look at what's called the adjoint representation of big GLN on little GLN, which is given by conjugation. And then you just take the derivative of that at the identity. So one natural way to generalize Lie algebras is by writing that exact same definition and then literally just deleting the word alternating. So a left Leibniz algebra is a vector space equipped with a bilinear map called a Leibniz bracket, such that if you fix the left variable in your bracket, then you get a k derivation. And so in particular, a Lie algebra you can define as just being an alternating or skew-symmetric Leibniz algebra. And you can also define right Leibniz algebras similarly. And of course, you have then a homomorphism of Leibniz algebras, which is just a linear map that is compatible with bracket. Okay, so as an example, you have what's something called the omni-Lie algebra, which is kind of a terrible name because it's not actually a Lie algebra. But it's denoted by a little OLN, and as a vector space, it's just GLN direct product with k to the n. And the bracket is given in the first variable by the commutator, so the same Lie bracket as GLN, and the second variable by having the left matrix act on the right vector. And you can check that this is actually a Leibniz algebra, but it's only a Lie algebra if n equals 0. Okay, so what is a coquecigrue problem? Well, Leibniz algebras were, well, they were first introduced in 1965 by Blow, but they didn't really become popular until Loday reintroduced them in 1993. And in that paper, Loday asked the question, he asked the following question. Um, so there's a way to geometrically interpret a Lie algebra as being the tangent space at the identity of a Lie group over RC or an affine algebraic group over any field. So then the coquecigrue problem asks, so then what geometric object should play that role for Leibniz algebras? With the stipulation that since the algebras are a subcategory of Leibniz algebras, then our geometric object should somehow recover the fact that there's a functor from Lie groups to Lie algebras. So in other words, there should be something in this corner here such that this diagram commutes. So one solution to this comes from surprisingly comes from a algebraic object, another non-associative one that was originally introduced in knot theory. So in the 1980s, Joyce and Matveev independently introduced things called quandles, and then 10 years later, in the 1990s, Fenn and Rourke reintroduced, they introduced a generalization of those called racks. So I'll just go over the definition in a minute, but these are algebraic structures that are, in a certain sense, invariant under the three Reidemeister rules from knot theory, or in the case of racks, only two of these. I won't go over that, but I will go over this definition. So in 2007, Pekinian made the observation that a rack can be defined as a structure with a binary operation such that if you fix the left variable, then you get an automorphism. And that morally should be similar to the fact that for a Leibniz algebra, you can define that as a vector space with the multiplication such that if you fix the left variable, then you get a derivation. And then he wanted to add a point, so a unit to give you like a point that you can take the tangent space at to get a Leibniz algebra. So with all that motivation in mind, we can define a pointed rack to be a set Q, a distinguished element E, which I'll call the unit, and a binary operation on Q, such that for each fixed X, the left multiplication map by X is an automorphism that fixes E. So by an automorphism, what I mean is that it distributes over your rack product triangle, and that it's a permutation of Q. So in particular, you can also define a rack as being like a left distributive magma such that each left multiplication map is bijective. And then we just need to add a point to it that's fixed by all the left multiplication maps. And one more axiom that we want left multiplication by E to be the identity. So in other words, E is going to be fixed by all the left multiplication maps, and left multiplication by E is going to fix everything else. So as an example, every group induces what's called a conjugation quandle, a quandle being an idempotent rack, with the rack operation given by conjugation. And the unit here is the same as the unit of the group. Okay, so then we can define a Lie rack to be a pointed rack such that the underlying set is a manifold and your rack operation is smooth, and then what's your so-called inverse rack operation is also smooth. Note that this definition, in particular, the fact that each LX is a permutation, can also be phrased equivalently as saying that there's also an inverse rack operation. That's what I mean by triangle inverse. So we require those to be smooth maps, and we require Q to be a smooth manifold. So as an example, every Lie group induces a smooth conjugation quandle. As a more non-trivial example, you can take what I call the omnilinear rack, or big OLN, which is just a direct product of CLN and R to the N, or C to the N, or K to the N, or what have you, as a set or as a manifold. And then the rack operation is given by conjugation in the first variable, and the second variable by having the left matrix act on the second vector. And if this reminds you of the Leibniz algebra, little OL and the Loday-Lie algebra, then it should, because it turns out that the tangent space of big OLN at the natural unit really is little OLN. Okay. So one of Kenyon's theorems is that the tangent space of a Lie rack at the unit is in fact a Leibniz algebra, and this also makes a diagram commute. So to sketch the proof, you do a similar thing where you define adjoint representations, and then once you've done that, for each element of your tangent space, you're going to take a smooth path that starts at 0 and that differentiates to that tangent vector. Then you write down the left distributivity axiom, which is one of the defining axioms of a rack, and you differentiate it with respect to each of the 3 variables, each at 0. And because a conjugation quandle, because each Lie group induces a smooth conjugation quandle, then what we get is that we get this functor here, and we get that this diagram commutes over R and C. So that's great. I should also note that many authors also add to this problem by saying, okay, so by making it also into an integration problem, is there an inverse functor from Leibniz algebras to X? And that's a natural thing to ask over R or C, because over those fields you have what's called the Lie-Cartan theorem, sometimes called Lie's third theorem, which states that if you look at the full subcategory of simply connected Lie groups, then this functor is actually an equivalence of categories. And so then you can ask an interesting question, is there something similar for Lie racks and Leibniz algebras? So I won't be discussing that today, because if you replace Lie groups and manifolds with affine algebraic groups and schemes, then you don't even have any kind of Lie-Cartan theorem for groups. So there's no hope of having an integration for Leibniz algebras. But that is an interesting question, so I did want to mention it. Okay. So there's kind of a general principle that notions in differential geometry should have some kind of analog in algebraic geometry. And sometimes the relationship between those notions is more than just an analogy. So, for example, an equivalent way of defining a Lie group is by saying that it's a group object in the category of manifolds. So similarly, you can define, if you replace manifolds with schemes, so you can work over a field K or literally any commutative ring K, then you can define an affine algebraic group to be a group object in the category of affine schemes. And so then you can ask a similar question here. So it does turn out that the tangent space, there are a few definitions of tangent space in algebraic geometry, but for whichever one you use, there is a functor from affine algebraic groups to the algebras over K. So then you can ask the same question, can I define something over here that's going to make this diagram commute? Now, it seems like this should be the case, and it is, but it's a lot harder because we don't have smooth paths and like nice differentiation techniques like we did earlier for Lie racks. But it turns out that this construction does still work. In fact, we even have this very nice formula. I'll explain the notation for this later, but the Leibniz bracket can be literally just constructed by this map, what I call nabla, and that's a homomorphism of k-algebras that is induced by your rack operation. I'll go over that notation later. But this does work. In fact, if you take K to be R or C, then this actually recovers Kenyon's theorem for algebraic Lie racks. So in other words, Lie racks that you can describe using only polynomials. Yeah, and of course you get the commutation of this diagram because again, conjugation quandle of an affine algebraic group will be an affine algebraic rack once I define what that is. So how do we prove this when we don't have the techniques of differential geometry? So we're going to have to juggle between a few different definitions of tangent space and algebraic geometry. So one of them being derivations from the so-called coordinate ring of an affine scheme to the ground field, and then looking at the algebra of dual numbers, which is kind of an analog of linear approximations in calculus. And this actually, the construction will turn out to be similar from to the functor from affine algebraic groups of the algebras. But then checking that it all works does take a bit of work. So the main focus of this presentation is going to be on that theorem, getting from affine algebraic racks to Leibniz algebras, but there are actually a few more motivations that we can talk about too. So one, it's interesting. It would be interesting to study affine algebraic racks just like in their own right, because in differential geometry, you have Lie groups and you have Lie racks, and you can study those. In algebraic geometry, you can study affine algebraic groups. So then it's natural to ask if there's a way to similarly to just study the theory of affine algebraic racks. So that's one motivation for doing this, is not only just for the coquecigrue problem, but literally just what is the notion of a Lie rack in algebraic geometry. Another motivation is that it comes from knot theory. So if you have a knot or a link, call it L, and you have a Lie group or an algebraic group G, then you can define something called the representation variety of that link, which is all the group homomorphisms from the fundamental group to G. And that turns out to be an algebraic variety. So in other words, a scheme with some very nice properties. Now, in the 1980s, Joyce and Matveev introduced something called the fundamental quandle of a link. And it turns out that there's a certain adjunction between groups and quandles, such that this set of homomorphisms right here is the same as the homomorphisms of racks from the fundamental quandle to the conjugation quandle of the group. So then, therefore, if we replace conj of G with any algebraic rack or Lie rack, then we get a very natural generalization of this. And in fact, this does turn out to be pretty useful. I've added a reference here to a paper by Gonzalez, Prieto, Martinez, and Munoz studying that. And then yet another motivation is applications to the Yang-Baxter equation from statistical mechanics. I'll talk a bit more about that later. But there are some authors who are interested in studying solutions to the Yang-Baxter equation in the category of varieties over C or other fields. So looking at Yang-Baxter solutions in the category of schemes is a natural generalization of that. It turns out that you can use affine algebraic racks or rack schemes more generally to construct those solutions. I'll talk about that later. First, to finally define what an algebraic rack is, I'm going to start with a quick algebraic geometry primer. So as a convention, other than Leibniz algebras, all my algebras are going to be commutative, unitable, and associative over K, which is a field, but you can take it to be a commutative ring, and most of this will still work. So one way to define an affine scheme, which is going to be our notion of a manifold here. And you can define more generally a scheme that's not affine, but for this presentation, we're just going to stick with the affine case for simplicity. So what is an affine scheme? So you take a k-algebra, I'll call it A, and then you construct two things. So one is a topological space called spec A, or spectrum of A. And as a set, that's a set of prime ideals of A, but then it's equipped with a topology called the Zariski topology. And then the second thing, denoted by O, so that is a sheaf of localizations of the coordinate ring of your affine scheme. In other words, A, at each prime ideal of A. And then if this affine scheme has certain nice properties, then it's called an affine variety. So as an example, affine space, or AN, is a variety with coordinate ring, a polynomial ring, and n variables. Now, the guiding principle here is that the functor that sends an affine scheme to its coordinate ring, so in other words, that sends spec A to A, should be a contravariant equivalence of categories. That does turn out to be true And you can define intrinsically what a morphism of schemes is, but because of that, for this presentation, we'll just define a morphism of affine schemes to be the dual of a k-algebra homomorphism between the coordinate rings. So for example, you have the closed embedding of the circle into your affine plane, and that embedding is the same as dual of this projection here, this ring projection from your polynomial ring of two variables, which is the coordinate ring of the affine plane, to this quotient of it, which is the coordinate ring of the unit circle. Okay, so later on, Grothendieck noted that by Unita's level from category theory, an affine scheme is the same thing as a representable functor from algebras sets. So namely, if you have a scheme X, an affine scheme X, then you can look at its R points for each k-algebra R. So this is a set with coordinates, and that allows you to talk about like an affine scheme using like coordinates. So as an example, affine space, as we saw earlier, if you think about that as a functor, then it just sends R to R to the n. Here are a couple more examples. So one is the multiplicative group variety. So this is noted by GM, and it sends a k-algebra R to its group of units. Its coordinate ring is the ring of Laurent polynomials. Actually, that's a typo. R should be replaced with K here. As another example, the general linear group variety, or GLN. So as a functor, that just sends R to GLN of R. So in other words, all the invertible matrices over that. As a variety, its coordinate ring has. Oh wait, is my audio working? Sorry, 1 second.
Yes, yes. Yeah.
Okay, am I still audible? Something happened to my audio.
We can hear you.
Okay. Okay, I think the audio is working now, but yeah, let me know if something happened. So GLN is an affine variety with coordinate ring given by this. So in other words, it's given by the matrix entries and then the inverse of the determinant. That's saying that the inverse of the determinant should exist. So both GM and GLN are affine algebraic groups. That's because they factor through the forgetful functor from groups of sets as functors. So then similarly, we can define an affine algebraic rack as a scheme such that if you look at it as a functor, then it should factor through the forgetful functor from pointed racks to sets. And there are a couple like equivalent definitions of this. So as an example, so affine algebraic groups you can also define to be a group object in the category of affine schemes. And then it turns out an affine algebraic rack defined this way is the same as a so-called pointed rack object. You need to define what that is, but a pointed rack object in the category of affine schemes. So as an example, every affine algebraic group gives you a conjugation quandle scheme with the unit just being the unit of the group. And then you have the omnilinear rack variety, that's what I call it, or OLN, which is the product of GLN and affine space. And it has the same pointed rack structure as before. So these are the same as the two examples that I gave earlier for Lie racks, but just adapted to work over any field. Okay, and then here's yet another equivalent definition. So I noted earlier that the functor that sends an affine scheme to its coordinate ring is a contravariant or equivalence of categories, right? So then you can ask, so if I have an affine algebraic group, what are the algebras that are associated to those via this functor? And those turn out to be exactly the commutative Hawk algebras. So then you might ask the same about affine algebraic racks. So since an affine algebraic rack is a pointed rack object in the category of affine schemes, so what that means is that you have a scheme with these two scheme morphisms, so triangle and triangle inverse. and then your unit, which you can view as a morphism from the ground field to your scheme. And then you just take the duals of those. So I'm going to call the duals of triangle and triangle inverse nabla and nabla inverse. It's kind of inspired by the fact that for a Hopf algebra, you use capital delta. And then EL turn into E sharp. So you can just write, you can write down the equations that are formally dual to the rack axioms, and then this gives you another equivalent definition of an affine algebraic rack. We will use actually. So here's yet another example. So you can say that you have an algebraic group that acts on a scheme. And then say that you also have a map from your scheme to the group that is compatible with the units, and that's compatible with the action in this way given here. So then you can define something called an augmented algebraic rack by equipping Q with this rack structure that's given by your map and your action. And this definition I basically stole from the definition of an algebraic or an augmented Lie rack, but just adapted it for manifolds of schemes. But what's nice about using schemes is that now we can consider spaces that have singularities. So now I can construct some pretty unique rack structures on spaces with singularities. So as a more simple example, just as an example, consider the ring that's this polynomial ring over the dual numbers. So if you look at its spectrum, then that's an affine scheme that we call the thickened line. So geometrically, you can visualize this as just a line with some infinitesimal thickening around it. So in coordinates, what that means is that if you have a k-algebra R, then the set of R points, Q of R, is given by these tuplets, where the first coordinate is an R and the second coordinate squares is 0. So in particular, if R is reduced, then you just get you basically just get affine space again, but R need not be reduced. So you can actually get a more interesting structure out of this. So if you can consider the action of GM on Q with weight 1 and -1. So in other words, have it act by multiplication on the first coordinate and then multiplication by the inverse in the second coordinate. And then you take this map here. And so you can check that this satisfies the axioms of augmented racks. And so this turns the thickened line into an algebraic rack with this operation right here. And then by the slides from before, this is equivalent to saying that you have k-algebra homomorphisms, nabla inverse, and then E sharp, which is right here, that are given by these formulas. And I should say also, this is by far not the only construction you can do using this scheme. In particular, if you work over characteristic P, then you can look at actions of the algebraic group of P roots of unity on Q. And it turns out you can also get algebraic rack structures from that. Okay, so now we've defined what affine algebraic racks are. Let's talk about the main theorem here that addresses the coquecigrue problem. Okay, so since we're trying to look at the tangent space of an affine algebraic rack at the identity, we're going to need to juggle between few different notions of tangent space and algebraic geometry. So the one that's in the theorem is as the vector space of derivations from the coordinate ring of your scheme to the ground field. Derivations meaning that they satisfy the Leibniz rule with respect to E sharp. So E sharp being the homomorphism of k-algebras that's induced by your unit. So then looking at this vector space, and I'm going to call it math_frac Q. That's kind of just inspired by the fact that if you have a Lie algebra of an affine algebraic group or a Lie group, then you notate it by math_frac G. So I'm going to put math_frac Q with these two brackets here. So this is going to be a left Leibniz bracket, and this is going to be a right Leibniz bracket. So as a reminder, Navla here is the k-algebra homomorphism that's induced by your rack multiplication triangle, and then similarly for Navla inverse here. All right, so those are nice formulas, but if we want to get the theorem to work, then we need to be able to describe these formulas in a few different ways. So in particular, we can try and mimic the construction of the functor from affine algebraic groups to the algebras. And that's by looking at the so-called adjoint representations. So similarly here, so because of all the axioms that we had on the unit E, we can look at, so for each morphism of affine algebraic racks, so in other words, a morphism of schemes that's compatible with the rack operations, then we can look at its derivative at the identity, which is just given by a pullback. So because of the way that we define an affine algebraic rack, each point in your scheme induces the left multiplication map, which is an automorphism of that scheme. So then therefore, the derivatives of that at E, because of the axioms that we had about E, are also going to be vector space automorphisms of math Q. So therefore, we can associate to each point in your scheme the adjoint representation that's just given by the derivative of that left multiplication map. And then what we do to try and get a Leibniz bracket is then we then take the derivative of that, and that's what we call little ad, or this adjoint representation of math frac Q, and that's just the derivative of this at the unit. And in particular, if Q is a affine algebraic group, then the left multiplication maps are just conjugation. But for an affine algebraic group or Lie group, the adjoint representation literally is conjugation. And so because of this, if we can get this all to work, then this will automatically recover the theorem for affine algebraic groups and Lie algebras. So in other words, it's a direct generalization of that, if we can get this to work. Problem is that when we do define it this way, then the codomain of this second adjoint representation is going to be this vector space of derivations, which is the same as a tangent space of but the problem is that what we want in order for this to work nicely is we want to be able to identify this with little GL of Q. So in other words, all the matrices over Q. And these are isomorphic, but the isomorphism between them, we need to also translate all this data across that isomorphism too, and that actually does take a bit of work. So to do that, we're going to pass through yet another isomorphism. So another way of defining a tangent space is by using dual numbers. So this is kind of your analog of linear approximations in algebraic geometry. So this proposition is saying that there is a way to identify the tangent space with a certain subset of R points of your scheme, where R is the algebra of dual numbers. So that's what all of this is saying, if you translate it. So this bijection between math frac Q to the tangent space, I'm going to call that partial. Okay, so these are the tools that you can use that we're going to use to prove this theorem, which I'll give an outline for. But as a reminder, the theorem is that the pairings that we defined earlier are make Q into a left Leibniz algebra and then a right Leibniz algebra. And then, therefore, we get a functor that makes the diagram from the coquecigrue problem commute. So as an outline of the proof, so given a tangent vector in Q, so in other words, a derivation D, so I'm going to look at partial of D, and then by this proposition, I can then view partial of D as an R point of Q, where R is the algebra of dual numbers. And then using that, I can compute normal forms for these maps. So in other words, these are if you look at these as R points of Q, then because of that, those induce some k-algebra isomorphisms or automorphisms, L partial D, that are related to the left multiplication maps from earlier. And then you can, so yeah, those are, I guess technically those are scheme automorphisms, and then you can look at the induced k-algebra automorphisms, which are L partial D sharp. So once you have normal forms for those, then we can try to use isomorphism partial to identify the adjoint representations we constructed earlier with the Leibniz brackets. I put quotes around here because we're needing to do a bit of identifications. But to do that, you need to compute the coefficient of epsilon in your adjoint representation as dual numbers. So in other words, like these are dual numbers, and so we need to find the coefficient of epsilon in those. And it turns out that those are precisely what these are. So the point of doing that is that that shows that this is the same construction that actually Kenyon used for Virax, just in a different language. And it shows that the diagram from earlier commutes. That said, we still need to check that this is a Leibniz algebra, and to do that, instead of looking at the scheme, since we're working with affine schemes, and it's the same as working with the coordinate rings because of the equivalence of categories, instead we're just going to look at the coordinate rings. We're going to look at the k-algebra homomorphisms that are induced by your scheme morphisms. So in other words, nabla and E sharp. And through a lot of calculations, you can recover the Jacobi identity from that. And then compatibility of morphisms, so functoriality is just a fact, it's just the chain rule. But then you also have to show that morphisms of algebraic bracts get sent to Leibniz algebra homomorphisms. And that is just a direct check. But yeah, so that might seem like kind of convoluted, but that does seem to be in like the easiest way to circumvent the problem that we don't have smooth paths, and so we can't just take derivatives like over and over again like we did with manifolds. All right, so here's an example to show how that works. So as a reminder, earlier I had what I called the omnilinear rack variety. So that's OLN, and as a scheme, that's the product of GLN and affine space. And then we know from if we think of this as a Lie rack over RC, then the tangent space is little o of n. So how do we prove this for arbitrary fields? Well, this theorem says that the diagram from the coquecigrue problem commutes. So because of that, we know that the Leibniz bracket of the tangent space has to agree with the Lie bracket of GLN on the first variable, and that's a commutative. So then this reduces to computing how the bracket on the second variable. So to do that, so first we'll write the coordinate ring of OLN as a tensor product of the coordinate rings of GLN and AN. The AN part is given by these T1, Tn, so in other words, polynomial ring and n variables. And we just have to compute what the bracket does to each of these things. All right, so this is going to be a direct computation. So first, we're going to need to work out what nabla of each of those coordinates is. Again, nabla is induced by the rack operation. So that's a direct computation. And it turns out that you get this expression for that. So then if you take an arbitrary bracket and you have it act on Tj, so x, v, y, w, then it turns out that you get the jth coordinate of xw. So having that, since that's true for all j, then you get this formula here, which is exactly the definition of the Leibniz bracket of little o, and the omnium algebra. So that is how you prove that analog of the OLN example over RC over arbitrary fields. All right, and then you can also ask, what are the properties of this functor? What can we say about the Leibniz algebra of an affine algebraic rack if we know some stuff about the affine algebraic rack? So one nice thing is that this functor sends closed subracks to Leibniz subalgebras, and you can also define a left ideal and a left center of a rack. And it turns out that this functor also preserves those things. Um, so in other words, like this functor is very compatible with the structure of an affine algebraic rack. In the same way that the functor from affine algebraic groups, the algebras, is. Um, you can also ask, under what conditions is a Leibniz algebra of an affine algebraic rack going to be abelian? So in other words, when is the bracket uniformly zero? So a sufficient condition is that your affine algebraic bracket is involutory. So in other words, if you compose two left multiplication maps together, then you get the identity, and that you're not working over characteristic two. So as a corollary, if you take Q to be the conjugation quandle of an affine algebraic group, then you get this result, which is for an affine algebraic group over characteristic not two, then if the square of every element is central in the group, then the Lie algebra is abelian. And this is actually not too hard to show like directly, but this proposition gives us a very nice way of generalizing that to affine algebraic racks. And then it's a very natural question of, okay, what other things from the theory of algebraic groups and Lie algebras can we generalize to algebraic racks and Leibniz algebras? So that is another interesting question to explore in future research. But instead, I'm going to talk about applications to the Yang-Baxter equation, which is an equation coming from statistical mechanics, also called the Braid equation. So first, let me talk about it in the category of sets. So you have a set, and then you have a map R from x2 to x2. And we usually want R to like be a permutation. Then we can talk about the Braid equation, which is this equation here, where the Rij's are just R applied to the ijth components. So then so this is the category. So pairs of X and R are what we call either set theoretic solutions to the Yang-Baxter equation or braided sets. And then this definition generalizes pretty naturally to arbitrary monoidal categories, where you have an object X and then an automorphism of X squared R that make this diagram commute. And this diagram is literally just the Braid equation. And then you can define a morphism of Yang-Baxter operators, which is exactly what you'd expect. It's just a morphism that's compatible with R. And those were a category called YB of C, so Yang-Baxter operators. So it's pretty well known that if you have if you have an abstract rack, then you can turn it into a set theoretic solution of the Yang-Baxter equation using this formula here. So in other words, you first swap the variables, and then you take multiplication in the second coordinate. And you can check that that gives you a Yang-Baxter a braid set. So then it was shown that this construction also works for over arbitrary categories, arbitrary monoidal categories. I'm only working over Cartesian monoidal ones, though. And then what I showed is that this functor is also fully faithful, which I'm sure someone's proven that before, but I couldn't find a reference to that. But so in other words, like the category of rack objects in a category is a full subcategory of Yang-Baxter operators of that category. Now, the reason why I put this in quotes is because for an arbitrary category, you don't have elements or coordinates, so you can't really write this down like this. Instead, you have to write it down in terms of morphisms. But it all works out. So in particular, if we take C to be the category of schemes or affine schemes, then what we get is that every affine rack scheme then induces a Yang-Baxter operator in affine schemes, which is given by this. But then, because affine schemes and k-algebras are contrariantly equivalent, and since this diagram is actually invariant under reversing arrows, then you also equivalently get a Yang-Baxter operator in the category of k-algebras. So in other words, a k-algebra where this Yang where a Yang-Baxter operator whose underlying set is a k-algebra, and such that R is like a morphism. And then if you take any k-algebra R and you look at the R points of Q, then you get a braided set. In other words, you turn the R points of Q into a braided set by just like turning this R into a function on the set. So as an example, if you have an algebraic group, then we can look at its conjugation quandle, and then we can consider the corresponding Yang-Baxter scheme. So as a scheme, we'll look at this as a functor from algebras to braided sets. And so this sends a k-algebra R to this braided set here. This should actually be G of R. But the formula for the Yang-Baxter operator is the same as the one given here. So you just swap the variables and then conjugate the second one. So in particular, if G is affine, then you can translate this into also a Yang-Baxter operator in algebras. So for an affine algebraic group, the coordinate ring has a Hopf algebra structure. And so using the Squeezer notation for Hopf algebras, then you can work out that the corresponding Yang-Baxter operator on algebras is given by this formula. Okay, as a bit of a messier example, let's look at OLN, omnilinear rack varieties. So the corresponding Yang-Baxter scheme is defined on R points by, once again, flipping the coordinates and then using the rack operation on the second coordinate. So this formula. And then if you work out the math, then you can compute that the corresponding Yang-Baxter operator whose algebra is given by the tensor product. So in other words, the coordinate ring of OLN, then you get this formula for the Yang-Baxter operator. So the advantage of this is that probably you would not think of this formula like on your own. So if you want to construct Yang-Baxter operators in schemes or algebras, which you might actually want to do if you do algebraic geometry, for example, then you can just start with the rack scheme and then look at its corresponding Yang-Baxter operator. And you'll get crazy formulas like this. Okay, and finally, closing remark, here are some suggestions for future work. So I already mentioned that there's an interesting question of what stuff from the theory of affine algebraic groups and Lie algebras can be generalized to affine algebraic racks and Leibniz algebras. In particular, we can ask which Leibniz algebras are algebraic. So in other words, for which Leibniz algebras does there exist an affine algebraic rack whose tangent space is that Leibniz algebra? And this is already a hard problem for Lie algebras, but now it becomes even more interesting for Leibniz algebras. Also, the structure theory of affine algebraic groups, especially if you're working over an algebraic closed field, is very well studied. So then it's natural to try and ask, can you do the same for algebraic racks? Similarly, you can try and ask, how can we classify algebraic racks? And you probably want to limit yourself to looking at, connected ones, affine ones, lead ones, etc. I do have an upcoming paper that looks at a few classes as well, actually. You can also ask, so I've linked this paper here that talks about so-called omni-representations of Leibniz algebras. So these are just Leibniz algebra homomorphisms from math Q to OLN. And then we know from earlier that if you have an affine algebraic rack with tangent space Q, then a homomorphism from that to OLN, big OLN, the derivative of that will then become an omni-representation. So then therefore, maybe we can look at an omni-representation theory for affine algebraic racks that's related to the omni-representation theory of Leibniz algebras. There's also, I should mention, a separate representation theory for racks where you just look at homomorphisms into the conjugation quandle of GLN. And that's also interesting. We can also try and define that too. another one thing. Can you define an analog of functional cohomology for algebraic groups or algebraic bracts? I have no idea how to do this, but I think that would be cool. And some more applications. Earlier, we talked about representation varieties of knots. So this it would be interesting to try and study this generalization of those. In particular, in algebraic geometry, you can study algebraic knots, which are a way to construct knots from these schemes. And then recently, in like the past like decade or so, racks and quandles have actually found a lot of use in arithmetic geometry for various reasons. So it would be interesting to try and look at the applications of algebraic racks of those too. If anyone is interested in these questions, please feel free to reach out. I'm always looking for collaborators. But yeah, these are my references. Thank you very much.
Thanks, Luke, for the wonderful talk. So any questions or comments from the audience?
Oh, I can't hear. Sorry, one second. The audio isn't working for me.
I'm audible now? Am I audible? Any questions or comments? Am I audible, Luke?
Yes, the audio is working for me now. Sorry about that.
All right. I see. Any questions from the audience? All right. So maybe I have a naive question. So for racks, you can define the structure group, right? Which, if you look at the solution level, correspond to the structure group of the solution.
Mhm.
So, I mean, for an affine algebraic rack, the structure group will have what? Affine algebraic group structure or something?
This is an interesting question. I've been thinking about this too. I am it's not obvious to me what the structure sheaf of it would be. Um, so I'm not sure, and this would be an interesting question. Can you like put a scheme structure on the structure group? So I don't know. Great question.
Yeah. Because it happens when we look at the solution induced by a skew brace, then the structure
Mhm.
group inherits the structure of a skew brace. So I was just wondering what happens in case of the solution arising from affine algebraic racks. Yeah.
Mhm. Yeah, I don't know. I think it would probably be pretty non-trivial to construct the structure sheaf, but it would be interesting to see if you can do it.
Yeah. Thanks. All right. So I don't see any questions in comments also. All right. So let us thank the speaker for the wonderful talk.
All right. Thank you very much.
Thank you so much.